Okay, so let's look at problem 1.2.10. Now, the numbering in the book's a little different, but this just means chapter 1, section 2, exercise 10. Okay, so we're asked to use vector methods, meaning we're going to want to use vectors to do this. We don't want to take full recourse to, geometry or things like that. We should be using vectors as the items by which we're demonstrating this. So use vector methods to show that a parallelogram is a rectangle if and only if its diagonals have the same length. So we understand what a parallelogram is, right? That each side is parallel. Not each side is parallel, but you have two sides that are parallel and another two sides that are parallel. So in that case, if we have a parallelogram, we could say that one side is formed, let's use v, by this vector v here. And another side, we'll use blue for this, is formed by this vector u here, right? And then if I put another v up here, and I put another u right here, we have a parallelogram, right? Okay, so where we're going to go with this is we're going to show that the case when this is a parallelogram, meaning that the angle here has to be 90 degrees, which is the same as saying their dot product is equal to 0. That should be logically equivalent to having the same length diagonals. So to that end, here's what we're going to do. We're going to notice that one of the diagonals is going to be this one right here. This is going to be v plus u, right? And if I were to, I guess I should just draw it out then. If I had another one, and this might be done a little sloppy, folks, I'm not an artist. Okay, there's another u, and there's a v, right? Then what would be the case is that this diagonal right here would be v minus u, right? The idea being, okay, this is clear, v plus u gets us from v plus u, right? The other way around would be, okay, this thing right here, remember we start at the tip, this is the tail, so you can think of it as a vector sort of oriented this way. That's the other diagonal, the v plus u is oriented that way, right? So this is v, because we're at v here, minus u, this is where the tail should be, so we're at u here. So v minus u is this diagonal, and v plus u is that diagonal. And now what we're going to show is, okay, if, or maybe I'll say when u and v are not equal to 0, we have, so let's assume this isn't like a degenerate case where this just collapses into a point or anything, or a line. We have an honest to goodness parallelogram here. Then when v plus u, its length, is equal to v minus u, this length, right? So we're saying this diagonal is equal to that diagonal in length, Well, if these were equal, their squares would be equal, right? Okay, so we know that the square of a norm is just the dot product of the vector with itself. So if I'm squaring this norm, v plus u norm squared, then that's really just this vector, v plus u, dotted with itself. Equals, okay, same thing goes here, so we're going to have v minus u dotted with itself, right? And now dot products, they work a lot, they're linear, right? So they're going to, I can do v dotted with v, v dotted with u dotted with v, u dotted with u. So v dotted with v is going to be the norm of v squared, right? That's what, the same thing here applies, right? Okay, and then I'm going to skip over this little piece right here. I'm going to move over here. U dotted with u is the norm of u squared, right? And now look, we've got a v dot u and a u dot v, but it's commutative. U dot v is the same as v dot u, it doesn't matter. So this is really just two v dot u's, right? It's just two. Equals, let's do the same thing over here. Using the same reasoning, we're going to get norm of v squared. And now this time it's going to be minus because we're going to have a minus u dotted with v. So I can sort of pull out the minus. And then a minus u dotted with v, pull out the minus again. So it's a v dot u minus minus, right? So it's a minus v dot u and a minus v dot u. So that's a minus 2 v dot u. And then a minus minus is a plus. U dotted with u is a norm of u squared. Okay, and now look what we've got here. So these could cancel, and now look, I have a 2v dot u equals a minus 2v dot u. So something equals its negative. There's only one thing that equals its negative, and that's 0, right? So since the 2 is not 0, it must be the v dotted with u. And that completes the proof. That's it. So let's just kind of take a second here and kind of go through what we wrote and see the logic on this. So really this line is just saying, let's assume we have an actual parallelogram. Now, what this is saying is it's saying, okay, whenever this norm, the norm of the one diagonal is equal to the norm of the other diagonal in square, you're going to find this is a trick that you're going to play a lot with norms. You're very rarely going to be actually using the norm itself. It's just always, typically, not always, but it's typically much easier to use the square of the norm. So a lot of times we're just going to square it because it's easier to work with. Okay, so if the square of one diagonal is equal to the square of the other diagonal. So I don't put a bunch of if and only ifs, because this is if and only if, right? This is true if and only if that is true, if and only if that is true, if and only. But since these are all equalities here, I don't really need to put if and only if, because it's established sort of by the equality. All I'm really doing is expanding out the sides. I haven't really changed anything. So what we're doing is we're sort of starting with this assumption that they have the same length. You could kind of think of it as that. And that's true if and only if this, we just expanded out this. If and only if this, we just further expanded that out. And what we saw was that this thing right here, everything cancels out except for the 2vu and the minus 2vu. Well, as we said before, the only way that could be is if the v dotted with u is 0, but v dotted with u is 0 is the same thing as saying that v and u are perpendicular, right? So, sorry, perpendicular. Yeah, so that they're perpendicular. And that's what makes it a rectangle. A rectangle would be when the v and the u were perpendicular, which is what we wanted to show. So this establishes then that having the same length of diagonal means that you must be rectangle and vice versa. All right, thanks.